Okay, let's unpack this. Imagine for a moment if the universe had a kind of ghostly blueprint, an invisible dynamic structure that basically dictated how everything we can see forms and moves. What if the whole grand tapestry of galaxies, this cosmic web, wasn't just built on the matter we see, but was like constantly being sculpted, influenced by something, well, far more active than we usually think? Today, we're doing a deep dive into a really fascinating perspective that suggests exactly that, a universe shaped profoundly by something called dark plasma. Our sources for this are really centered around the work of Jay Alfred. His ideas, well, they challenge the conventional views of dark matter. He's proposing it's not just inert stuff, but a dynamic, maybe even electrically active part of the cosmos. So our mission today is to explore how this dark plasma universe might be the fundamental template for, well, everything from the biggest cosmic filaments down to how galaxies rotate. It potentially offers a unified explanation for some really big cosmic mysteries.
That's right. And what's so intriguing about Alfred's work, I think, is that it goes way beyond just saying dark matter is missing mass. He's really putting forward this idea that dark matter isn't passive, it's not inert, it's a dynamic, active dark plasma. And that could fundamentally reshape how we understand cosmic structure, how it evolves. He talks about this ghost universe concept or a template, where dark matter isn't just hanging around, it's an active participant. It provides the gravitational blueprint, sure, but also these hidden energetic dynamics coming from these dark sectors that, well, guide the visible universe.
Okay, so to kick us off, what's the foundational idea Alfred presents about this ghost universe?
Yeah.
How does it really differ from our standard picture of dark matter?
Well, Alfred's core idea is that the visible universe has this sort of mirror image, this ghost universe of dark matter acting as its template. Picture it like this. On the grandest cosmological scales, this dark plasma isn't just sitting there passively. No, it's actively influencing how structures form. And it does this through its own variations in density, temperature, even things like viscosity. And crucially, these dynamic, invisible dark structures then shape and organize ordinary matter structures, but only through gravity. So while we often talk about dark matter's general gravitational influence, Alfred's specifically saying it's the dynamics, the internal physics of this dark plasma that's doing the real work, not just its static mass.
Okay, building on that then.
Yeah.
We know computer simulations, things like gravitational lensing, they consistently show this cosmic dark matter web, right? These huge invisible filaments stretching across the universe.
Yeah.
How does Alfred's dark plasma idea fit with that scaffolding?
Yeah, his hypothesis is actually pretty elegant. If this cosmic web is dark matter, and if that dark matter is in a plasma state, well, then the threads of this web must be made of dark plasma. Ordinary matter is then just gravitationally attracted to them, sort of draped over these dark structures. But what's really fascinating is how Alfred details the dynamics within this dark plasma. He suggests these dynamics cause the dark filaments themselves to rotate, and as they rotate, they gravitationally tug on the ordinary matter filaments lying on top of them, making them rotate too. We've even seen hints of this, observations of things like vortexes, Mach cones, which are like cosmic sonic booms, and shock fronts in dark matter distributions, and some elliptical galaxies show faint traces of concentric shells. Alfred argues all of this points towards underlying dark plasma dynamics, and intriguingly, he connects it to the presence of something called dark Birkeland currents.
Hold on, dark Birkeland currents. Now, Birkeland currents, we know them from things like Earth's auroras, right?
Yeah.
But what exactly would dark Birkeland currents be in this cosmic picture?
Excellent question. So yeah, ordinary Birkeland currents are these powerful, self-organizing electric currents that flow along magnetic field lines. They often form these helical, rope-like structures. On Earth, they funnel charged particles from the sun down into our atmosphere, creating the aurora. In Alfred's dark plasma model, dark Birkeland currents would be essentially the same kind of thing, but made of self-interacting charged dark matter particles. They generate their own helical magnetic fields around them, and here's the crucial part. Their electromagnetic effects, the direct push and pull of electricity and magnetism, wouldn't be felt by ordinary matter. We wouldn't see them electromagnetically. Their influence on us, on the visible universe, would be purely gravitational, like a subtle, invisible hand shaping the cosmos.
Oh, okay.
So the key insight really is that the cosmic web isn't just a static gravitational framework. According to Alfred, it's a dynamic, rotating system of dark plasma filaments actively transferring angular momentum to visible matter purely through gravity.
Okay, that's a powerful idea. But the mechanism, how this dark plasma is different and why that difference matters, that feels like the really crucial part. What are the key distinctions Alfred highlights. What makes dark plasma behave so differently from the plasma we understand?
Right, this is where it gets really interesting, yeah. Alfred outlines several core differences. He suggests that dark sectors, while maybe similar to ours in having most matter in a plasma state, would likely have a higher rate of ionization. But crucially, and this is key, he posits that the fundamental electric charge of these dark particles is significantly weaker than the charge of our electrons and protons.
Weaker.
Yeah, weaker. Now, think about ordinary plasma. The strong electric charges mean particles interact very quickly, very aggressively, and any separation of positive and negative charges gets neutralized almost instantly. Zap, back to neutral. But Alfred argues that with a weaker charge, these dark particles interact less intensely. This effectively suppresses the plasma instabilities that would normally erase charge differences very quickly. And what that allows for is persistent, long-lived separations of positive and negative dark charges on large scales.
Huh. So a weaker charge actually makes charge separation more stable, longer lasting. That feels, well, it feels counterintuitive based on how electricity works in our world. How exactly would this sustained charge separation actually happen in dark plasma?
That's a great point. It is counterintuitive, but it's really fundamental to Alfred's whole model. He points to a whole suite of forces and instabilities that could drive this. Things like gravitational stratification, just heavier dark particles settling differently than lighter ones, mechanical forces like friction between different flows, fluid dynamical forces, just the complex motion of the plasma itself. He also mentions specific plasma physics effects, like the Weibull instability. That's where magnetic fields can kind of spontaneously generate themselves in plasma if the particles aren't moving uniformly in all directions. And the Biermann battery effect? Think of that like a natural cosmic generator. If you have temperature and density gradients in the plasma that aren't perfectly aligned, it can naturally drive electric currents and thus separate charge.
Okay, so multiple mechanisms potentially at play.
Exactly. And there are others too, like Langmuir turbulence waves sloshing around in the plasma. Even quantum fluctuations in the very early universe could have seeded tiny primordial magnetic fields, which would then separate charges via the Lorentz force. That's the force a magnetic field exerts on a moving charge. Plus, more exotic things like cosmic strings or domain walls, if they exist, could potentially trap or repel charged dark matter particles. And then there's the Pennicoke-Rosseline effect, which is basically gravitational stratification again, but specifically in a plasma environment causing charge separation. So the core idea, the takeaway, is that unlike our ordinary matter universe where everything rushes back towards electrical neutrality really fast, Alfred suggests dark plasma has this unique combination of properties, especially the weaker charge and suppressed instabilities that makes sustained, widespread charge separation not just possible, but maybe even the fundamental engine driving its large-scale dynamics.
That's quite a list of possibilities. So if this dark plasma can sustain charge separation, that opens the door to some really exciting consequences, right? Like the formation of weak but long-lived dark currents. Walk us through how Alfred sees these currents shaping the cosmos.
Exactly. If you have sustained charge separation, you can have sustained currents. According to Alfred, these self-interacting charged dark matter particles would flow, creating those dark Birkeland currents we talked about. These currents would generate helical magnetic fields around themselves, and they would tend to organize into what he calls nested helical Birkeland currents. Picture these like nested spiraling tubes of current, which would then naturally outline and form nested concentric shells of dark matter particles.
Okay, nested shells.
Right. And here's the key point again. Alfred stresses that the dark electromagnetic effects of these currents, the direct magnetic forces and fields, would stay confined within the dark sector. They wouldn't be felt directly by ordinary matter. Our ordinary matter universe would only feel their gravity. Now, what's really intriguing is how these dark currents and shells connect to things we can observe, especially cosmic rotation. Basic plasma physics tells us that structures like these nested, current-carrying shells would naturally tend to rotate. Alfred proposes this is the hidden dark mechanism driving the large-scale rotating cosmic filaments that observatories like ESA's Herschel have actually detected.
So it's like an invisible rotating electromagnetic framework underneath everything, and it just gravitationally pulls the visible stuff along with it. Can you give us a more concrete example of this gravitational tug in action?
Absolutely. The idea is when structures made of this dark plasma, like dark matter components of galaxies or even hypothetical dark matter stars governed by these dark Birkeland currents when they rotate, they gravitationally tug on the ordinary matter stars and gas that are mixed in or nearby. Alfred points to evidence right here in our own Milky Way. We live in a barred spiral galaxy, and observations suggest its central bar rotates more slowly than you might expect compared to the spiral arms. One leading explanation for this slowness is precisely the gravitational drag, or tug, from a massive rotating dark matter halo surrounding the bar.
Interesting.
So Alfred's overall picture is that the strength of the electric charge in these dark sectors might be sort of fine-tuned strong enough to allow for these large-scale dark electrical and magnetic activities, creating structure and rotation within the dark matter itself, but weak enough that its primary influence on us, on ordinary matter, is almost entirely through gravity. It's like a hidden electromagnetic ballet driving the cosmic dance we see.
That's a really compelling image.
Yeah.
Okay, so if this dark plasma is the universe's underlying scaffolding, defining these filaments and currents, how does it actually build something as huge and complex as a galaxy? Alfred offers a mechanism for that, involving something called the pinch effect. Sounds rather dramatic.
Yes, the pinch effect is definitely a cornerstone of how galaxies might form in this model. It's a well-known plasma physics phenomenon. As those dark Birkeland currents, which Alfred sees as the dark matter component of cosmic filaments, flow along their magnetic field lines, the current density can increase in certain regions. When the current gets stronger, the azimuthal magnetic field wrapping around the current channel also gets stronger. And this circular magnetic field exerts an inward Lorentz force, literally pinching or compressing the plasma filament.
Okay, it squeezes itself.
Exactly, it squeezes itself. Alfred's theory is that when these cosmic filaments, made of this self-interacting dark plasma, undergo this pinch, they can generate what's called a plasmoid. You can think of a plasmoid as a sort of self-contained blob or structure of plasma and magnetic fields, often kind of toroidal or bubble-shaped and usually very hot. This pinch process dramatically raises temperatures and creates a significant overdensity of dark matter right there at the pinch point. And that overdensity creates a deep gravitational well. Ordinary matter then naturally falls into this well, accreting onto the dark matter structure and forming the beginnings of an embryonic galaxy. He even suggests this process could be intense enough to form a supermassive black hole right at the center from the very beginning.
Wow. Okay, so the pinch creates the seed. But what about rotation? Rotation is absolutely fundamental to most galaxies we see, especially spirals like ours. How does rotation arise from this pinching process, in Alfred's view?
Right, that's the next crucial step. The dynamics get even more intricate here. Alfred explains that within these dark currents, you have oppositely charged dark particles flowing, often in opposite directions along the filament. This sets up conditions for magnetic shear layers sliding past each other and magnetic reconnection, where magnetic field lines break and reconnect, releasing a lot of energy. Then, another important plasma effect comes into play, the Hall effect. In this context, the Hall effect essentially introduces an asymmetry into the system during the pinch and plasmoid formation. It causes these newly formed plasmoids to start spinning. It effectively converts some of the directional energy of the inflowing current and the tension in the magnetic fields into rotational coherence, generating vortical motion, a swirl.
So the spin is kind of built in from the start.
Alfred proposes this as an additional inherent cause for the rotation of galaxies. The dark matter plasmoid starts spinning due to these plasma effects, and because the overlying ordinary matter is gravitationally coupled to it, the whole system, dark and visible matter together, begins to rotate. And intriguingly, recent observations and sophisticated simulations do confirm that the actual filaments of the cosmic web exhibit coherent rotation and vortical motion over enormous scales, like millions of parsecs. They seem to act as reservoirs of angular momentum for galaxy formation.
So observations are lending some support here.
It seems that way. Alfred highlights these findings, suggesting they fit naturally within his dark plasma framework. He also points to interesting alignment observations, like massive dark matter halos found at the ends of filaments tend to correlate with more rotation, and how large galaxies often seem oriented perpendicular to their host filaments, while smaller ones might be aligned parallel, possibly due to secondary, smaller filaments feeding them. It all reinforces his core belief that dark matter wasn't just cold and inert in the early universe. It remained a plasma, and its plasma dynamics actively sculpted the dark cosmic web structure, including imparting spin.
Okay, this really brings us to one of the biggest, most persistent mysteries in all of astrophysics, those flat rotation curves of galaxies. For decades, we've known that stars way out in the spiral arms of galaxies are moving much faster than they should if you only account for the gravity of the visible stars and gas. How does Alfred's dark plasma theory tackle this head-on?
Yeah, this is arguably one of the most powerful applications of Alfred's model, because the standard model needs to invoke these very specifically shaped massive halos of inert dark matter, just to explain this one observation. Our expectation that stars should slow down further out comes directly from applying Newton's laws to the visible matter we see. But Alfred says, wait, the dark matter isn't inert because dark plasma in his model is self-interacting via these electromagnetic forces and distributed differently, likely in these rotating currents and shells around the baryonic disk. Its gravitational influence doesn't just drop off sharply with distance, like the gravity from a central lump of mass would.
How does that work exactly? How does it maintain the gravitational pull further out?
He elaborates that a rotating dark Birkeland current, along with its surrounding plasma shells, inherently maintains a more distributed mass-energy density. This is partly due to electromagnetic tension, the magnetic fields resisting being compressed or stretched, and pressure within the plasma itself. These internal forces within the dark plasma structure essentially counteract the natural tendency for the gravitational influence to fall off rapidly with radius. And the result? You get coherent rotation across much larger distances. Stars way out at the edges are gravitationally held just as effectively as stars closer in, causing them to orbit at nearly the same speed, and boom, you naturally produce the flat rotation curve that we observe.
That really does sound like a potential breakthrough. It's not just adding more invisible mass. Alfred's model seems to provide a dynamic, self-regulating mechanism within the dark plasma itself that intrinsically explains why these rotation curves are flat. That turns a decades-old puzzle into a natural consequence of the theory. You mentioned lab analogies earlier.
Indeed. Alfred points out that this is quite analogous to how scientists observe magnetized plasma filaments behaving in laboratory experiments. They often maintain rotational coherence across their radius. This is sometimes explained by something called E cross B drift, where the combined effects of electric E and magnetic B fields force charged particles to move together in a very coordinated way, maintaining that consistent rotation speed across the filament. So he proposes that a rotating dark Birkeland current in space, possibly organized into an ensemble of these dark concentric prolate ellipsoidal shells, think elongated nested football shapes embedded within a galaxy's overall dark plasma halo, could naturally produce this flat rotation curve effect for the ordinary matter disk sitting within it.
Okay, prolate ellipsoidal shells.
Right, for spiral galaxies. But he clarifies the geometry might differ. In a more spherical galaxy, you might not see distinct shells within the main dark halo itself, but perhaps shells forming around the central baryonic component due to interactions. Whereas in a giant elliptical galaxy, maybe you'd get more spherical concentric shells encompassing the whole galaxy. But the key insight remains. Alfred's model offers a physical, self-interacting mechanism within the dark plasma that generates the necessary gravitational pull profile for flat rotation curves, rather than just assuming an inert dark matter halo happens to have exactly the right shape and density profile needed.
That explanation is incredibly powerful for such a persistent cosmic puzzle. Okay, well, let's push this further. Let's delve into even more specific, maybe even weirder galactic observations that Alfred's dark plasma model might explain. What about counter-rotation? Some galaxies have populations of stars rotating in opposite directions. Yeah. How does his theory account for that?
It's another fascinating aspect, yeah. His model provides a pretty neat mechanism for this. Remember how charged particles spiral around magnetic field lines? Well, positive ions and negative electrons spiral in opposite directions because of their opposite charges. Now, imagine there's also an electric field present along those magnetic field lines. This might happen naturally in structures called double layers, which are like sharp boundaries within a plasma where charge separation gets concentrated, creating a strong local electric field. This electric field will accelerate the charged particles along the magnetic field lines, but again, it pushes positive ions one way and negative electrons the opposite way. This creates what plasma physicists call bidirectional currents, flows going in opposite directions simultaneously within the same region.
Okay, flows going both ways.
Exactly. And Alfred explains how these counter-streaming flows can naturally lead to the formation of counter-rotating plasma structures, maybe manifesting as nested current shells, with adjacent shells rotating in opposite directions. He then suggests that this underlying dark plasma dynamic could be the reason we observe counter-rotating stellar populations in some galaxies, for example, where the stars in the main disk rotate one way, but stars in the central bulge or the extended halo rotate the opposite way. The dark plasma sets up the counter-rotating gravitational template, and the visible matter just follows suit.
That's a really specific, quite peculiar observation to potentially have a physical explanation for. Okay, this raises an important question when we look at elliptical galaxies too. Gravitational lensing, deep imaging, often reveals these incredibly faint, almost ghostly concentric shells around them. Galaxies like NGC 7600, NGC 3923 are famous examples. Sometimes they see, 20 or more shells extending way beyond the visible starlight. The standard explanation usually involves galactic mergers, right? Like a big galaxy swallowing a smaller one, and the leftover stars kind of slosh around and create these ripples or shells. But Alfred offers an alternative, doesn't he?
Precisely. The merger model is the prevailing one, but it sometimes struggles to explain the sheer number and regularity, the almost perfect symmetry of some of these shell systems. They look less like messy splash patterns and more like, well, onion layers. Alfred argues, and I'm quoting him loosely here from his writings, that the dark matter halo is not all collisionless and inert, but includes a self-interacting dark plasma component. This forms concentric shells of dark matter particles through plasma instabilities, double layers, and standing wave patterns. He was emphasizing this way back in 2005, noting the presence of shells in dark matter around galaxies suggests its plasma state. This is strong evidence that dark plasma is involved in interactions which can be modeled by using standard plasma.
So the shells form within the dark plasma itself first.
That's his proposal. These shells are natural structures that arise from the internal dynamics of the self-interacting dark plasma, things like instabilities, or the formation of those double layers we mentioned, or even standing wave patterns within the plasma halo. These dark matter shells then act as gravitational templates. They create slight variations in the gravitational potential, and over time, they gently tug the ordinary baryonic matter stars and gas into alignment, forming the visible concentric shells we observe through lensing or deep imaging. This explanation could potentially account for their amazing symmetry and persistence without needing a very specific, relatively recent, and sometimes dynamically complex merger event.
That is a really powerful alternative. But of course, Alfred's whole theory essentially reframes the very nature of dark matter. How does he address the prevailing scientific consensus, which largely treats dark matter as collisionless and inert? What makes his dark plasma model, in his view, a more compelling explanation for these highly structured features like shells?
That's the crux of the debate, isn't it? It's true, the standard cosmological model, lambda CDM, relies heavily on dark matter being cold, slow-moving, and collisionless, interacting primarily through gravity. Alfred's strength, however, lies in the model's potential explanatory power for phenomena that are kind of awkward or require special tuning within that standard inert model. These shells are a prime example. For Alfred, the shells aren't an accident of history, like a merger remnant. They are an intrinsic feature generated by the physics of the dark plasma itself. He's saying the dark plasma halo isn't just a smooth, passive blob, it's dynamically active, and it naturally forms these structures, shells, currents, filaments, due to its inherent properties, like instabilities and those charge separation effects. It's a bottom-up, self-organizing process within the dark sector. And the beauty, he argues, is that these pre-existing dark structures then simply gravitationally sculpt the visible matter, explaining the observed forms like shells, their symmetry, their persistence, without needing continuous violent events. It's a fundamentally different picture, yes, but he argues it's a potentially more coherent one when you look at the detailed observations.
So wrapping this up, what does this all mean for how we think about the cosmos? Jay Alfred's theory, this idea of a dark plasma universe, it really seems to provide a remarkably unified framework. It potentially connects the dots between cosmic web formation, galaxy rotation, those stubborn flat rotation curves, and even really peculiar structures like counter-rotating stars and those elliptical galaxy shells. It vividly brings back that idea we started with, the ghostly blueprint, a dynamic, active, dark plasma universe that's fundamentally shaping the ordinary matter universe we see, primarily through its pervasive gravitational influence, but driven by its own hidden electromagnetic life.
Exactly. And if we connect this to the bigger picture, Alfred's work really pushes us to wonder, doesn't it? What if the universe we perceive, the one filled with the stars and galaxies we can directly observe, is just, well, the visible manifestation of a far more complex, far more electromagnetically active dark realm operating underneath? How might accepting this perspective, seeing dark matter not as inert ballast but as a dynamic plasma, fundamentally change how we search for new physics, how we interpret cosmological data, how we understand the forces that truly govern reality? It leaves you, I think, with a profound sense of wonder about all the unseen forces and the hidden architectures that might be truly structuring our universe, possibilities brought to light by these intriguing theories from Jay Alfred.